Okay, so we just finished talking about this example, which is related to this picture. And this is supposed to give us, we put in a point and the time, and we get out a vector that's supposed to tell us the motion of a liquid. And then she points out that you may have noticed that this expression for v here is considerably more complicated than those for the functions given in 4 through 8. Well, actually, not quite true. But 4 was equally as complicated. But here, this one was not complicated in the same way, because she's saying that we don't see the individual components. Whereas here we actually do see the individual components. And here we don't see the actual components. But in this example, we do see the individual components, the I, J, and K. Well, in the first example, maybe there weren't any individual components. But anyway, so that's what she's pointing out. This is because all the variables and vector components have been written out explicitly here in this case. In general, if we have a function from Rn to Rm, then when x is an element of here, can be written like this, and f can be written in terms of its component functions. So this is given in terms of its component functions. So what we mean is there's a component for the I, for the J, and for the K. This is a function to R3, so we have three what we could call component functions. So here we have these three component functions. So this is one of them. So we could give this a name. Now, this one here, we mean not including the I, not including the J, not including the K. So just the variables that relate to the input. So x, y, z, t here, x squared minus y squared here, and 3z plus t here. So we could give these a name, like I could call the first one f1. f1, which is a function of x, y. Okay, so here's, we could call it f of x, y, z, t, and it's just the product of those. So this is f1 is this component, and f2 would be this component, and so on. Now notice that each of these components, like this one here, is a function from R4 to R. So the component functions are always functions into R, not some larger R2, R3, or something like that. So this is a function into R, this is a function. So we could say that this V consists of F1 times I, F2 times J, F3 times K. And again, F1, F2, F3 are functions from Rn to R. So here we have F, its input is a vector in Rn, so they write it out explicitly here. And then we can write the component functions. So this is F1, so this is F1. It's a function of x from Rn, but its output is just a scalar. This is our F2, which maybe in this case would be here. And then all the way up, we could have, instead of being a function into R3, we could have it be R4, R5, whatever. So we could have m component functions. So this is what she means by the component functions. The component functions F1, F2, up to Fm. The component functions are scalar valued functions of the vector x. The inputs are from here, but the component functions, the outputs are just R, not Rm, just R. right? This is just a function. This is just, the result is just a scalar here. So it's just a function to r. And altogether, they define the components of the vector f of x. So why do they call this the vector f of x? Because this is the function f, which is, well, in this case, it's into R3. So it's an element of R3. This is an element of R3. In general, we would say it's an element of Rm. She says, well, this gets quite messy because we write f of x, and then x can be written out like that. And then we could say this is the component functions. And then we could even write out that each component function is a function of these, because x is these. So we can write it out like that. And then we can look at an actual example. Okay, so this is what is meant by the component functions. Now, we may not have been paying attention, but she's using a notation where whenever the function is not a scalar valued function, so this is generally not a scalar valued function, but of course we just said this is a scalar valued function. Anyway, she's using the notation, if you go back and look, whenever it's a not scalar valued, she uses a boldface f. Okay, in other words, when the output is a vector, she uses the notation that the name of the function will be bold-faced. So this one is a function from x, which is in Rn, to Rm. So this should be bold-faced because it's to Rm. If we go back and check some of these examples, so this is also a function from x, from say R3 to R3. So anyway, the output is not a scalar, so she uses a boldface here. Now this one was a function from Rn to R, so that is scalar valued, right? It's just the length, which is a number. So you give it a vector, but you get a number. So this is a scalar, so she doesn't use bold for the name of that function. Going back to this one here also, it goes from R3, so the inputs are vectors, but the output is just a scalar, so she doesn't use a bold t here. Now she says, let's go back to the length function that we just looked at, and can we write it out in its components? Now the length function, we wrote it succinctly like this, just the norm of x. But we could also write it in terms of the components of x. Not the component functions, because there's only one function, but we could write it in terms of x, the components of x, the elements of x, I should say, I guess. So it's L of x equals L of this, and then in terms of these things, these variables, it's the square root of the sum of the squares of these. That's what you get when you do x dot x. X dot x square root, the norm of x. This is what the norm of x is. This one also was written succinctly like this, but we could also write this like this, and then the norm like this, just like we did here. The norm like that. And then we could even write it in, now this though, okay, this one was scalar valued. L was scalar valued. Notice L is not bold, but this one, N, is bold. So we have to express it as a vector. It is expressed as a vector here. It still is expressed as a vector here because this is a vector divided by a scalar is a vector. And then here we actually write out the components of the vector. So it's x1 divided by this, x2 divided by this, x3 divided by this, like this. So we see the components, and these are again called the component functions. This is the first component function, f1 maybe, f2, f3. And they are scalar valued functions, not vector valued functions. And instead of calling them f1, f2, f3, we could call them n1, n2, n3. So n1 is this one, n2 is this one, n3 is this one, and n1, the inputs are vectors, but the output is a scalar, as before. So then she says, although writing a function in terms of all of its variables and components has the advantage of being extremely explicit, quite a lot of paper and ink are used in the process. The use of vector notation not only saves space and trees, but also helps to make the meaning of a function clear by emphasizing that a function maps points in Rn to points in Rm. So you could write it this way, and that gives you a certain insight into it. And you could write it this way. That gives you a different insight into it. So there are different reasons to do it, to write it in one way or the other. Vector notation makes a function of 300 variables. So this could be a function of 300 variables because x could be from R300. Look just like a function of one variable. So it still kind of looks just like a function of one variable, even though it's in R300. Try to avoid writing out components as much as you can, except when you want to impress your friends. Okay.